Imagine a universe that hums with secrets, whispering clues about its origins through invisible waves, blinding flashes, and ghostly trails of antimatter. Out there, among the stars, strange phenomena challenge everything we think we know about the cosmos. From a mysterious radio signal pulsing every 22 minutes for decades, to dazzling blue explosions that outshine entire galaxies, to ripples in space-time that echo the Big Bang itself, the universe is alive with puzzles waiting to be solved. Let's embark on a journey through these cosmic enigmas, unraveling their mysteries with vivid storytelling and the latest discoveries as of August 29, 2025. Buckle up, because this adventure will spark your curiosity, tug at your sense of wonder, and leave you eager to share your thoughts in the comments below. Picture this, it's 1988, and somewhere in the vastness of space, a signal begins pulsing toward Earth, arriving every 22 minutes with uncanny precision. Fast forward to 2022, when astronomers using the Murchison Wide Field Array in Australia stumble upon this cosmic heartbeat, now known as GPMJ 1839-10, located 18,000 light years away. At first they assume it's a pulsar, a neutron star spinning rapidly, beaming intense pulses of light like a cosmic lighthouse. But as they dig deeper, analyzing 35 years of archival data, they uncover something extraordinary. This signal has been ticking with near-perfect stability since at least 1988, its rotation period of 21 minutes and 58 seconds barely wavering by more than 0.28 milliseconds over 3 decades. For a pulsar spinning so slowly, this stability is unheard of, challenging the very laws of stellar physics. Neutron stars, the ultra-dense remnants of massive stars, are the densest objects in the universe, save for black holes. Imagine a star 1.4 times the mass of our sun, squeezed into a sphere the size of Manhattan. A single teaspoon of its matter would weigh as much as 11 times the entire human population. 8 billion people. These cosmic powerhouses spin at dizzying speeds, some completing hundreds of rotations per second, their magnetic fields generating cascades of light and particles that beam across the galaxy. The process is mesmerizing. An electron near the star's magnetic pole accelerates, emitting a curvature photon that spawns an electron-positron pair, which in turn produces more photons in an exponential cascade. These beams sweep past Earth as the star spins, creating the pulses we detect with radio telescopes. But GPMJ 1839-10 is no ordinary pulsar. Most pulsars spin fast, their rotations slowing over time as they lose energy, eventually entering Death Valley, a state where their beams fade into silence. Yet this signal, pulsing once every 1,318 seconds, is over 1,000 times slower than typical pulsars, and its stability defies expectations. If it's a pulsar, it's shining brightly from beyond Death Valley, where no pulsar should glow. Could it be a magnetar? A neutron star with a magnetic field 10,000 times stronger than average. Magnetars can unleash starquakes, cataclysmic events that release energy as light. But starquakes are fleeting, and no X-rays expected from such events are detected from this source. A magnetar outburst lasting 35 years is simply unthinkable. What about a white dwarf, another stellar remnant with a magnetic field strong enough to produce radio emissions? White dwarfs are less dense than neutron stars, but even the most magnetic ones, like the pulsar Aosco, emit signals 1,000 times fainter than GPMJ 1839-10. Other possibilities, like interactions between stars and exoplanets or binary brown dwarfs, fall short too. Their emissions are 100 million times weaker. The signal remains a cosmic riddle, its source a mystery that could herald a new phenomenon. Astrophysicists are thrilled, knowing that such anomalies often spark revolutions in our understanding. More signals like this may lurk in existing data, waiting to illuminate the processes powering these cosmic beacons. What do you think this signal could be? Drop your theories in the comments and let's spark a discussion. As we ponder the enigma of GPMJ 1839-10, let's zoom out to consider the grand architects of the cosmos, the forces that sculpted galaxies, stars, and the very fabric of space itself. The universe, born 13.8 billion years ago in the Big Bang, was once a seething cauldron of energy, too hot for matter to form. Within moments, it cooled enough for protons and neutrons to coalesce. But it wasn't until 380,000 years later that light could travel freely, creating the cosmic microwave background, a snapshot of the universe's infancy. Yet the structures we see today, galaxies, clusters, and vast cosmic filaments, owe their existence to tiny quantum fluctuations in that primordial soup amplified by gravity over billions of years. These fluctuations, like ripples on a cosmic pond, set the stage for the universe's evolution, but their precise origins remain one of astronomy's greatest mysteries. Could the gravitational waves detected by nanograv hold clues to these ancient seeds of structure? The possibility is tantalizing, as these ripples may carry imprints of the universe's first moments, offering a glimpse into the physics of creation itself. Imagine decoding the blueprint of the cosmos. How thrilling would that be? Share your thoughts on what shaped the universe in the comments below. Now, let's take a moment to imagine the unimaginable. What would happen if you could stand on a neutron star? The sheer density of these objects creates gravitational fields 200 billion times stronger than Earth's. If you weigh 70 kilograms on Earth, your mass remains the same, but weight is a measure of gravity's pull. On a neutron star, that pull would multiply your weight by 200 billion, flattening your body to an atomic scale. Your atoms crushed into neutron degenerate matter, drop from just 1 meter above the surface, and you'd slam into it at 1,500 kilometers per second. The star's gravity is so intense that light itself can orbit it, creating a surreal view where you might see the entire star at once. Neutron stars are cosmic perfectionists, their immense gravity sculpting them into the universe's most perfect spheres, smoother than any object we know. A teaspoon of their matter weighs 4 billion tons, equivalent to 10,000 Empire State Buildings. This density comes from neutron degenerate matter, a state where atoms are stripped of empty space, leaving only neutrons packed tightly together. The thought of standing on such a star is a humbling reminder of the universe's extremes, pushing the boundaries of physics and our imagination. Have you ever pondered the forces shaping these stellar giants? Share your thoughts below. Shift your gaze to the Gemini constellation, 800 light-years away, where a pulsar named Geminga is bombarding Earth with antimatter. Discovered in 1972 as a gamma-ray haze, Geminga puzzled astronomers for decades. Named by Italian physicist Giovanni Bignami, its name, a play on Gemini and gamma, also means it's not there in his Milanese dialect, a nod to its elusive nature. Initially, its source was unknown, hidden among the stars. By 1983, faint X-ray signals narrowed the search, and in 1991, pulsing X-ray and gamma-ray emissions revealed Geminga as a pulsar, spinning 4 times per second. Unlike typical pulsars, Geminga is nearly radio silent, its faint pulses at 100 MHz barely detectable due to its magnetic field absorbing or refracting higher frequency radio waves. This pulsar, born from a supernova 350,000 years ago, is a cosmic speedster, racing at 210 kilometers per second toward the border of Gemini and Lynx. Its motion creates 2 X-ray tails stretching 3 trillion kilometers, formed by its dense mass, compressing the interstellar medium and accelerating particles to emit high-energy radiation. Geminga's most astonishing feat is its antimatter production. In 2011, NASA's Alpha Magnetic Spectrometer on the International Space Station detected an unexpected flood of positrons, antimatter counterparts to electrons. By 2013, it had recorded 400,000 positrons, a 100-fold increase in cosmic positron data. Initially, scientists hoped this signaled dark matter annihilation, but a 2017 discovery by the HWC Gamma Ray Observatory pointed to Geminga. Its gamma ray halo, spanning 20 degrees of the sky, suggests that this pulsar alone could account for 20% of the positrons reaching Earth. As it spins, Geminga's magnetic field accelerates particles, boosting starlight to gamma ray energies, creating a glowing halo visible from Earth. This revelation, confirmed by a decade of data from Fermi's Large Area Telescope, shows Geminga's halo as a cosmic spectacle 40 times larger than the full moon if visible to the naked eye. While it doesn't solve the dark matter mystery, it highlights pulsars' role in shaping the cosmos. Since Jocelyn Bell's first pulsar discovery in 1967, over 300 gamma-ray pulsars have been found, thanks to NASA's Fermi mission. Geminga, with its secrets unveiled, continues to push the boundaries of astrophysics. What other surprises might pulsars hold? Let us know in the comments. The discovery of pulsars, beginning with Jocelyn Bell's groundbreaking find in 1967, has transformed our understanding of the universe's most extreme objects. Initially mistaken for signals from extraterrestrial life, pulsars revealed themselves as neutron stars, their rapid spins and intense magnetic fields creating beams of radiation that sweep across space like cosmic lighthouses. Over the past 6 decades, astronomers have cataloged thousands of pulsars, each offering a unique window into stellar evolution. The Fermi Gamma Ray Space Telescope, operational since 2008, has been pivotal, identifying over 300 gamma ray pulsars by 2025, including outliers like Jaminga. These discoveries have refined our models of neutron star formation, revealing how supernovae compress massive stars into dense cores, their magnetic fields amplifying to trillions of times Earth's strength. Pulsars also serve as cosmic laboratories, testing theories of gravity and quantum mechanics under conditions impossible to replicate on Earth. As we uncover more pulsars, each with its quirks, like GPMJ 1839-10's slow, stable pulse, or Jaminga's gamma ray dominance, we edge closer to understanding the physics of the extreme. What new insights might the next pulsar discovery bring? Drop your predictions in the comments, and let's keep the cosmic conversation going. Now, let's tune into the universe's deepest hum, gravitational waves, ripples in space-time itself. Unlike light, which was trapped in the universe's early plasma for 380,000 years, gravitational waves have traveled freely since the Big Bang's first moments. In 2023, the Nanograv collaboration announced a groundbreaking discovery, evidence of a gravitational wave background, a cosmic symphony from supermassive black hole binaries and the universe's birth. Using 68 millisecond pulsars as a galaxy-sized detector, Nanograv measured tiny variations in their pulse arrival times. These pulsars, spinning millions of times per second, are the universe's most precise clocks. By correlating pulse variations across pairs of pulsars, researchers isolated the gravitational wave signal, revealing a Hellings and Downs curve, a hallmark of space-time ripples. With a 3 sigma confidence level, this evidence suggests a 1 in 1,000 chance of being a fluke, with more data expected to confirm a discovery. These ultra-low frequency waves, with wavelengths spanning tens of light years, are beyond the reach of detectors like LIGO, which senses high-frequency waves from colliding black holes. Instead, Nanograv's pulsar timing array acts as an interstellar interferometer, detecting the faint hum of galaxy mergers and primordial waves. This breakthrough opens a window to the universe's earliest moments, offering clues about black holes and the Big Bang. What secrets do you think these ripples hold? Share your ideas below and subscribe for more cosmic discoveries. Finally, let's chase the brightest explosions in the cosmos. Luminous, fast blue optical transients, LFBOTS. First spotted in 2018 by NASA's ATLAS telescope in Hawaii, these dazzling blue flashes outshine supernovae by 10 to 100 times, reaching peak brightness in hours and fading within days. Nicknamed the cow, koala, camel, and others, these events share a pattern: blue emissions, high luminosity across X-rays, ultraviolet and radio waves, and locations within galactic spiral arms. Perfect for massive stars that explode as core collapse supernovae. But LFBOTS defy expectations. The cow's emission spectrum showed broad lines and weak helium, unlike typical supernova. In 2022, the Tasmanian Devil pulsed repeatedly, each burst as bright as the initial explosion, suggesting a star that seemed to die and revive multiple times. Then, in 2023, the Finch exploded 3 billion light years away, far from any galaxy's spiral arms, shattering the supernova theory. 2 new hypotheses emerged. Could an intermediate mass black hole, shredding a star in a globular cluster, cause these blasts? Or might colliding neutron stars, producing a kilonova, be responsible? Without gravitational wave data from LIGO, which was offline, or detectable gamma ray bursts, the mystery persists. The Vera C. Rubin Observatory, set to begin operations in late 2025, will scan the southern sky every few nights, capturing more LFBOTS to unravel their secrets. These explosions, though rare, challenge our understanding of stellar life cycles and cosmic cataclysms. What do you think powers these cosmic fireworks? Drop your theories in the comments and hit that like button if you're as captivated as we are. As we marvel at these cosmic phenomena, let's reflect on the technology that makes these discoveries possible. From the Murchison Wide Field Array's detection of GPMJ 1839-10 to the Fermi Telescope's mapping of Geminga's gamma-ray halo, advanced instruments are our eyes into the universe. The Vera C. Rubin Observatory, nearing completion in Chile, will revolutionize our hunt for LFBOTS, capturing 10 times more light than its predecessors and scanning the entire southern sky every few nights. Meanwhile, the James Webb Space Telescope, operational since 2022, is probing distant galaxies and faint star clusters, potentially clarifying the Finch's origins. These tools, combined with pulsar timing arrays like nanograv, are pushing the boundaries of what we believe is possible, turning fleeting signals into profound insights. Each technological leap brings us closer to answering age-old questions about the universe's origins and evolution. What new tools do you think will shape the next era of discovery? Share your ideas in the comments, and let's imagine the future of astronomy together. Now let's dive into the cosmic ballet that shapes the universe's grand stage, the intricate interactions between stars, black holes, and other celestial bodies. The universe is not a static canvas, but a dynamic arena where objects orbit, collide, and merge, creating the spectacles we observe. Take binary systems for instance, pairs of stars or neutron stars locked in a gravitational embrace, spiraling closer over millions of years. When neutron stars merge, they can unleash colonovae, explosions so powerful they outshine entire galaxies and produce gravitational waves detectable by instruments like LIGO. These events, like the hypothesized cause of the Finch LFBOT, forge heavy elements like gold and silver, seeding the cosmos with the building blocks of planets and life. The dance of supermassive black holes at galactic centers, as detected by nanograv, creates low-frequency gravitational waves that ripple across light years, whispering tales of ancient galaxy mergers. These interactions are the universe's heartbeat, driving its evolution from chaotic beginnings to the structured cosmos we see today. Imagine the stories these collisions tell. What do you think the next cosmic dance will reveal? Drop your thoughts in the comments, and let's keep exploring. The mysteries we've explored, from GPMJ 1839-10's enigmatic pulses to the explosive brilliance of LFBOTs, are more than scientific puzzles. They're testaments to humanity's relentless curiosity. For centuries, astronomers have gazed at the stars, armed first with crude telescopes and now with cutting-edge observatories like the James Webb Space Telescope and the upcoming Vera C. Rubin Observatory. Each discovery builds on the last, from Galileo's sketches of Jupiter's moons to Jocelyn Bell's detection of the first pulsar, which opened a new window into the universe's extremes. Today, as we stand on the cusp of 2026, we're not just observing the cosmos but listening to it, decoding its signals through radio waves, gamma rays, and gravitational ripples. This quest unites us, from the researchers analyzing pulsar timing data to the dreamers pondering the stars from their backyards. It's a shared journey fueled by questions that have echoed through generations. What is out there? How did it all begin? As we uncover new phenomena, we're reminded that every answer sparks new questions, driving us forward. What inspires you to explore the cosmos? Share your passion in the comments, and let's celebrate our collective quest for truth. Looking to the horizon, the future of cosmic exploration is brimming with promise. By late 2025, the Vera C. Rubin Observatory will begin its mission to map the southern sky, potentially capturing dozens more LFBOTs and shedding light on their origins. The square-kilometer array, set to become the world's largest radio telescope by the late 2020s, will enhance our ability to detect faint signals like those from GPMJ 1839-10, possibly uncovering a new class of cosmic objects. Meanwhile, advancements in gravitational wave detection, building on nanograv's success, could soon pinpoint individual supermassive black hole binaries, revealing the dynamics of galaxy formation. The James Webb Space Telescope continues to probe the universe's earliest galaxies, offering clues about the cosmic dawn. These tools, combined with artificial intelligence to sift through vast datasets, are poised to transform our understanding of the cosmos. Imagine a day when we decode the full story of the Big Bang, or identify the source of every mysterious signal. How close do you think we are to that moment? Share your predictions in the comments and hit that subscribe button to join us on this journey into the unknown. As we unravel these cosmic mysteries, one puzzle looms larger than most: dark matter, the invisible substance thought to make up about 27% of the universe's mass energy. Unlike ordinary matter, dark matter doesn't emit, absorb, or reflect light, making it maddeningly difficult to detect. Yet its gravitational influence shapes galaxies, holding them together against the centrifugal forces of their rotation. When scientists first detected an excess of positrons with the alpha magnetic spectrometer, they hoped it might be a signature of dark matter annihilation, a clue to its nature. However, discoveries like Geminga's positron-producing halo suggest pulsars may account for much of this signal, leaving dark matter's identity as elusive as ever. Current theories propose dark matter could consist of weakly interacting massive particles, WIMPs, axions, or even sterile neutrinos, but experiments like those at CERN's Large Hadron Collider have yet to find definitive evidence. As we push the boundaries with new detectors and observatories, the hunt for dark matter continues to captivate scientists and dreamers alike. What do you think dark matter could be? Share your wildest theories in the comments, and let's dive into this cosmic conundrum together. The breakthroughs we've explored, from nanograv's gravitational wave detection to the identification of Elifbots, are not the work of lone geniuses, but of global collaborations uniting thousands of scientists across continents. The NANOGRAV project, for instance, involves researchers from institutions like the National Radio Astronomy Observatory and international partners, pooling decades of pulsar data to detect space-time ripples. Similarly, the Atlas and Zwicky Transient Facility telescopes, which spotted LFBOTs, rely on teams from universities and observatories worldwide, sharing observations in real time to capture fleeting cosmic events. The James Webb Space Telescope, a triumph of collaboration between NASA, ESA, and the Canadian Space Agency, exemplifies how collective expertise can unlock the universe's secrets. These efforts remind us that science is a shared endeavor, amplified by diverse perspectives and cutting-edge technology. As we look to the future, projects like the Square Kilometer Array, involving over a dozen countries, promise to deepen our cosmic understanding. How do you think global teamwork will shape the next big discovery? Drop your thoughts in the comments, and let's celebrate the power of collaboration. Beyond the science, these cosmic mysteries, pulsars, gravitational waves, and explosive transients, carry profound philosophical weight. They challenge us to confront our place in an unimaginably vast universe, where phenomena like GPMJ 1839-10's steady pulse or the Finch's solitary explosion defy our expectations. These discoveries remind us that the universe operates on scales and rules far beyond human experience, humbling us while igniting our sense of wonder. They ask, are we alone in this cosmic expanse? What does it mean to exist in a universe born from chaos, yet capable of such precise, awe-inspiring phenomena? As we probe deeper, from the Big Bang's echoes to the potential for new physics, we're not just seeking answers, but redefining the questions that drive us. These mysteries connect us to the cosmos, urging us to keep exploring, questioning, and dreaming. What philosophical insights do these cosmic puzzles spark for you? Share your reflections in the comments, and let's ponder the deeper meaning of our universe together. From the steady pulse of GPMJ 1839-10 to Geminga's antimatter shower, from spacetime's ancient ripples to the blinding flashes of LFBOTs, the universe is a tapestry of mysteries that ignite our curiosity. Each discovery pushes the boundaries of science, reminding us how much remains unknown. As telescopes like the James Webb and Vera C. Rubin peer deeper into the cosmos, we're on the cusp of new revelations. Join the conversation, share your thoughts, theories, and excitement in the comments below. Like, subscribe, and turn on notifications to stay in the loop with the universe's greatest enigmas. Together, let's keep exploring the wonders of the cosmos.